All right, so real quickly today we're going to take a look at how to verify inverses. This is a topic that you probably came across in your Algebra 2 course, and you might be a little confused about it, so that's why we're here, to go over it a bit. Now, I do want to give you a heads up, I'm using some slightly different technology. I'm mixing all this video together live, and then we'll post it directly. But, of course, you don't really care about that stuff. But I just wanted to give you a heads up. So let's get right to it. What on earth is an inverse, first of all? An inverse is where you have a function that's maybe you put numbers in. Like, let's imagine we put the number 3 into the x squared function. What happens when you square the number 3? You get the number 9. All right, that's great. Now, what happens if you say, oh my gosh, I did not mean to turn the 3 into a 9. How do I undo that? There is no undo button here, except there is. It's called the inverse, and that's where we go backwards by doing, quote, the opposite, right? Some students call it that, which is really the proper term, though, is inverse. We use the inverse, and then, which is just, we get the 3 back, which is the square root function here. The square root of x is called the inverse of the squaring function. So the way we notate that, by the way, is if f of x equals x squared, then we say the inverse function is the square root of the input, or x. So each of those x's represent where we put the numbers. Now, how do we verify two things are inverses besides just trying numbers like crazy, right? We could do that, but that's not really the best way to do it. So there's an actual proof that we use to verify that two functions are inverses. So I put together two quick examples for you. So here it says verify that 5x minus 2, we're calling that f of x, and a separate function called g of x, which is x plus 2, that quantity divided by 5. How do we verify that those two things are indeed inverses of one another? Well, here's what you do. Here's the proof, is you take the first function, f of x, and you put g of x on the inside of it. That's called composing a function, composition of function. So we're going to find f of g, and if we do a whole bunch of algebra, what we expect to happen is to get x out of that thing. And we're also going to do it the other way around. We're going to do g of f of x, and if we do it right, we should get a bunch of algebra, and then we'll get x. And this is basically what your work should look like. You should see it all work out to just be x. Now you might be wondering, how does that work, or why does that work? Well, going back to our example here, recall that I started with 3, and then I did something, and then I undid it, and then where was I at the end? I was right back where I started. This was my x, was my input, and then my x was right back where I started again at the end. So I'm right back to the x. So I ended up putting x in, I got my f of x, and then I did the inverse function, and then I'm right back to x again. So that's the meaning of these statements here, is that if you put g inside f and f inside g and work it out, you ought to just get x, that generic input number. So, folks, let's try it here. Let's try it. So here we go. F of g of x. So the f function is f times the input minus 2, right? This x is where we put things. Now, what are we putting in there? We're putting the g of x function in there. So I'll use a different color here so it stands out a little bit. X plus 2 over 5. Now you might be thinking, oh my gosh, that looks like a mess. What am I going to do with that? Well, the cool part is you know what should happen, right? It should work out to be x. And indeed it does, because look, 5 is actually 5 over 1, which means this 5 cancels that 5. So now I'm left with x plus 2 minus 2. See, this was the x plus 2 right here, and then here's the minus 2. And then what happens to the plus 2 and minus 2? They add up to 0. They cancel again, so we're left with x. And you put the little check mark there to say, hey, yeah, we did what we wanted to do. We got an x out of it. Now, we got the second part. A lot of students forget to do the second part. So g of f of x. So the g function is input plus 2 all over 5. And what are we putting in there? What are we putting in there? We're putting 5x minus 2 in there, and the parentheses are actually optional, so let me just delete them at this point. The parentheses really didn't need to be there because there was no distributive property. And you see how the 2 and the negative 2 add up to 0 again, and we have 5x over 5. And then the 5's cancel, and OMG, oh my goodness, the x appears again on that half. So we've proven what we want to prove here, that we have verified that the two functions are indeed inverses of one another. Now, when a teacher gives you a problem like this, I can guarantee, at least when I do it, and when any teacher that I've seen does it, they are inverses, and you will expect this to happen. When they use the word verify, that implies that they are inverses. Just show it. Okay, if it says determine whether they're inverses, then who knows? You don't know what's going to happen. All right, so I wanted to go through a second example where we have a square and a square root in the two functions, and we have to sort all that out. Believe it or not, I believe these two are inverses of one another. We're going to verify it. Let's use the exact same procedure. We're going to do f of g of x. Now, the f function is 4 times the input squared plus 1. And what are we putting in there? We're going to put our red function. I like to use lots of colors here, so we're going to call that g function is going to be our red function. We're going to put g inside f, so that means the square root function goes in here like this. And now what do we do? Well, it looks like a mess, but we're going to just simplify it using order of operations. So order of operations says do what's inside the parentheses first. There's nothing to do there here, folks. So then we move on to exponents, and I do see a square. So we're going to square this red fraction. And when we do that, let's see what we get. We get 4 times x minus 1 over 4 plus 1. When you square a square root, don't forget they just cancel. They just vaporize each other, and that leaves x minus 1 standing. Now, just like earlier, remember this is 4 over 1, so these 4's cancel, so this equals x minus 1 plus 1. Oh my goodness, there it is. It equals x, check mark. Now, are we done? No, of course not. We gotta verify that it also works in reverse. So we have to take our red function, our g function, which is the square root of the input minus 1 all over 2. And in there, we're going to put f of x, which is 4x squared plus 1. Didn't leave myself much room there, but there we go. Now, technically, those parentheses are optional, so let me try to delete those here. I'm going to delete that one and delete that one. Now, inside the radical, you see how those two add up to 0. They cancel each other. So we get the square root of 4x squared all over 2. Now, the square root of 4x squared, those are both perfect squares. So we get the square root of 4 is 2. The square root of x squared is x all over 2. And then the 2's cancel. And look at this. We're left with x. Boom. So it did work out. So indeed, yes, they are inverses of one another. So hopefully this wasn't too bad for you, and now you understand how exactly you can verify two inverses. This is something that comes up in Algebra 2, not too hard when you see a few of them, so you might want to practice a bit, and I hope you do well on your homework. Until next time.